Welcome everyone. Today we're going to be proving a very nice trigonometric identity as is shown here on board. But as you can see, it's not just a regular identity, it is what is called a conditional identity because there is a condition put on the arguments. Here the arguments alpha, beta, and gamma are positive and their sum is equal to pi. And in the title I call this a triangular identity because the sum of the arguments is pi, as is the sum of the angles of a triangle. We'll be covering two separate ways of proving this identity, one mostly algebraic and one mostly geometric way. In my opinion, the geometric one is more elegant, so make sure you stick around for that. And also, we'll be covering a lot of facts from trigonometry that you may not know, so it should be quite interesting. Let's get right into it with the algebraic method first. For the first method, we're required to use a few already established trigonometric identities in order to prove the one we want to. First four I've listed right here that I will be using. They are all quite basic and I hope not to go over them. However, the fifth one, it is one of the most foundational identities in our proof, and I doubt that many of you even know it. So we're going to derive it real quick right here. Say you have the sine of sum p plus q and you're adding it to the sine of p minus q. What will you get then? Well, we can use our identity for the angle sum. The first one will get sine of p times the cosine of q, then plus the sine of q times the cosine of p, and then the same thing here, however with a negative sine of q cosine of p term, because here there's a negative sign in the argument. And so these two will cancel out, and we will result with 2 times the sine of p times the cosine of q. Now, say you let p plus q equal to some single variable like x, and p minus q equal to y. Well, what will this now be equal to? Well, we simply have to find p in terms of x and y, and q also in terms of x and y. What will we get? We get that p is equal to x minus q. We know that minus q is equal to y minus p, so this is equal to x plus y minus p. Therefore, 2p is equal to x plus y, or p is simply half of x plus y. And the same can be done for q, which will take basically the same amount of time. It's going to be x minus p. We perform the same steps and find that q is equal to x minus y over 2. And look what we have just done. Because p plus q equals x and p minus q equals y, we found that the sine of some x plus the sine of some y is equal to 2 sine of p cosine of q, which we have found is 2 times the sine of p, x plus y over 2, and then times the cosine of q, so x minus y over 2. And we have just converted the sum of a sine, the sum of two sines, into the product of the sine and cosine. This is often called the sum to product identity. The sine of x plus sine of y equals to all of this. And this is going to be our fifth identity right here. This identity that we have just learned, called the sum to product identity, is going to be very useful to us because that's precisely what is going on with the problem. We have some sum of sines and we have to show that it's equal to a product of sines. So this is going to show up very briefly, but first we can do one more thing in order to make this problem a bit easier. Let's make use of our condition that alpha plus beta plus gamma equals pi. We can then isolate one of the variables, such as gamma, and show that it's equal to pi minus a plus b, minus that sum. We just move over the terms to that side. And this is now very nice because we basically have turned this into an identity of 2 variables instead of 3. So now let us make a direct transformation on the sum of the sines, the sine of 2 alpha plus the sine of 2 beta plus the sine of 2 gamma, which we have shown gamma is going to be equal to this. So twice of it is going to be 2 pi minus 2 times this alpha plus beta. And as I said earlier, we're going to make a direct transformation on this in order to get this right-hand side right here in our identity. First, we are going to use the sum to product on the sine of 2 alpha plus the sine of 2 beta. We're simply just going to use the identity that I've showed you at the start. We're going to get 2 times the sine of 2 alpha plus 2 beta over 2, and then times the cosine of 2 alpha minus 2 beta over 2. As you can see, this is quite simple because this just becomes the sine of alpha plus beta times the cosine of alpha minus beta. And then we're going to simplify this sine of 2 pi minus 2 times alpha plus beta. Because there's a 2 pi in the argument of the sine, 2 pi is the period of sine, so we can simply just ignore it and look at it as the sine of negative 2 alpha plus beta. So as we know the sine is an odd function, we can simply use its parity, and we get that's equal to the negative sine of 2 alpha plus beta. So that was basically 2 steps I did there at once. Hope you can follow along. We can keep simplifying this. We're going to get 2 times the sine of simply alpha plus beta, and then times the cosine of alpha minus beta. And this negative sine of 2 alpha plus beta, we can use the double angle identity on it, which we know is going to be 2 times the sine of alpha plus beta, and then times the cosine of alpha plus beta. So we got something extremely nice right here. And we can proceed to factor out 2 sine of alpha plus beta. It is here on both sides. So let us do that. It is going to equal 2 times the sine of alpha plus beta, and then times the first one in here, we got the cosine of alpha minus beta, and then here we got minus the cosine of alpha plus beta. We can then expand this using the cosine angle sum, so here we'll have the same twice sine of alpha plus beta, but inside we will have simply cosine of alpha times the cosine of beta, then plus the sine of alpha sine of beta, and then we're going to subtract, let me carry it here, subtract the cosine of alpha, the cosine of beta, and then we're also going to subtract a negative, which is going to become a positive sine of alpha, and then sine of beta. And this is very nice because the cosine parts cancel out, and we get twice sine of alpha, sine of beta. So this is going to equal 2, if we just multiply it out now, 2 times sine of alpha plus beta times 2 sine of alpha, sine of beta. And it's very close to resembling the form we want up here, because now we have a 4 times the sine of alpha times sine of beta, but also sine of alpha plus beta. So this very closely resembles the form we have right here. Just here we have an alpha plus beta instead of a gamma. But look, alpha plus beta is equal to pi minus gamma from our condition. And as we know, the sine of pi minus x is equal to the sine of x. That includes gamma. So this is basically just equal to 4 times the sine of alpha times the sine of beta, and then times the sine of pi minus gamma, which is equal to the sine of gamma. And we are done with the direct algebraic proof, because we have shown that our sum of sines from the start is equal to this 4 times the product of sines. Hope you all learned something from this sum to product identity for sines. I think it's quite interesting. And now let us move on to the geometric approach of solving this problem. The reason that this identity can be done geometrically is by the fact that the sum of alpha, beta, and gamma equals pi, which is precisely the sum of the angles in a triangle. So we can simply construct a triangle with angles alpha, beta, and gamma and proceed from there. So what can we do next? Well, since our identity involves a bunch of signs, my first thought is definitely the law of signs. So let us label these sides of this triangle accordingly. So A, B, and C, for example, and then use the law of signs on it. So A over the sine of alpha equals B over sine of beta equals C over sine of gamma. But there is another part to the law of signs that many forget or often don't really need, which is that all of these ratios are equal to twice the circumradius, twice r, or the circumradius of this triangle. So let us also draw a circle around this triangle. That seems like quite a good idea. I'll try my best here to make a circle. All right, and say its circumradius is somewhere right here. The circumcenter is right here, and then we can connect these lines to these line segments to each vertex of the triangle, which will equal the circumradius, these lengths. And for simplicity, for the sake of proving this identity, we can work with variables here, but let's have this r equal to 1. This will make all of our calculations much easier to work with then. Next, we can use the inscribed angle theorem. Notice how, say, this angle beta right here subtends arc AC. So it's going to equal half the measure of arc AC. But also, because our circumcenter is right here, this is going to be a central angle. The angle A to, say, O right here, which I can label AOC, is going to be a central angle, which also subtends AC, meaning its measure is going to equal arc AC, and meaning it's going to be twice of beta. Hopefully that all makes sense. And so we can say the same about all of these other angles right here. This one, which subtends arc AB, which uses angle gamma, this is going to be twice of gamma, and this one right here is going to be twice of alpha. So what can we do now? Well, remember one of the area formulas for a triangle, which is going to equal the one of its side lengths times the other side length times the angle between them over 2. So we can write out the area of this triangle ABC as, for example, half of AB times the sine of the angle between A and B, which is gamma. So where am I going with all this? Why do we need such area formulas? Well, notice we can write the area in another way. Since we have this circumcenter right here, we can write the area as the sum of 3 triangle areas. It's going to be these 3 isosceles triangles formed with the circumradius and also these angles to alpha, to gamma, and to beta. So area of ABC is also going to be 1/2 times the circumradius, or r squared, and r is equal to 1, times the sine of the angles between them. So sine of 2 alpha, and then we're going to sum up, because it's going to be one of these triangles, and we need all 3 of them. So 1/2 sine of 2 alpha plus 1/2 sine of 2 beta plus 1/2 sine of 2 gamma. And so we get that 2 areas of ABC, if we just multiply everything by 2, is going to be equal the first part of our trigonometric identity, the left side of it, the sine of 2 alpha plus the sine of 2 beta plus the sine of 2 gamma. All very nice. And how can we connect this to another area formula? Well, we can do just that. Notice that 2 areas of ABC is also equal to, for example, we can take our one with the sine of gamma. It's going to equal AB times the sine of gamma. And how else can we write AB? Well, it all comes back to our law of sines from the very beginning. A is equal to 2r times the sine of alpha, simply from proportions. As is B is equal to 2r times the sine of beta. And since we let r equal to 1, that's an arbitrary decision, we can write out this as the sine of alpha times simply 2 times 1. So this is going to equal twice the area of ABC. So it's going to be 2 times the sine of alpha times 2 times the sine of beta times the sine of gamma. And would you look at that, that is just equal to 4 times the sine of alpha times sine of beta times sine of gamma. And so we are done by transitivity. The area 2 times ABC, so twice the area of the triangle, is equal to both this, which is on the right-hand side, and also this, which is on the left-hand side. And so we have proved the identity by comparing the areas of these triangles. How nice is that? And so that is going to be it for today's video on a very nice trigonometric identity. Hope you all greatly enjoyed. Make sure to check out my other videos if you did, and I will see you next week on Wednesday.